Konnichiwa. I think that's hello in Japanese, not sure. This is going to be just the first 3 questions of your Chapter 3 stoichiometry notes. These are not going to be stoichiometry things. We've probably already talked a little bit about a mass spectrometer and how they use that to determine relative masses and abundances of isotopes of an element. So this is going to be just finding the average once you know all the different isotopes and their abundances. So I apologize for the bright light, but that's the way it has to work. So here's chromium has 4 isotopes. So it's giving you the 4 isotopes. Again, a mass spec would have determined these. Chromium 50, which actually has a mass of 49.946 AMUs. Remember atomic mass units. Remember that protons and neutrons are not exactly 1 AMU. That's why it's that way. But only 4.3% of all the chromium on the Earth are those ones. Okay, they've done study after study after study and figured out this is the percentage of chromium atoms that are that mass. The biggest percentage of chromium is this mass. Then you've got two other ones here. So to find the average, we can't just add them all up and divide by 4 because there's not equal numbers of them. So if I want to know the average mass of all the isotopes, I take the percent as a decimal times the mass. So 4.3% have this mass, 83.76% have that mass, 9.55% have that mass, and so forth. So there's those 4. So percent times mass plus percent times mass plus percent times mass, that would give you the average. And you can check your answer on the periodic table because the periodic table should have the average as well. So when you do this one, you get an average of like 51.99. And if you think about it, we should be pretty close to probably this one because the largest chunk of the isotopes are that. So again, it is, I'll make sure, yeah, it's 51.998 AMUs. That's a fairly simple one. Let's go down to one that's a little bit more difficult maybe. Antimony has 2 isotopes, 123 and 121. Okay, so 121 has a mass of 120.9 AMUs, and 57.25% of all the isotopes of antimony are that one. And then it gives you the average mass of all antimony isotopes. Well, we know the percent of this isotope is 57.25%, so 100 minus that, sp123 would be 42.75%. So pretty easy to get that percent. I don't know what this mass is. Obviously, it's going to be close to 123, 122 point something probably. But I do know the average. So the average of these isotopes and those isotopes, the average is that. So now I'm doing the same thing, but now I know the average. I can plug it into here. So I'm going to say, well, the average is 121.75 equals this percent times this mass, 0.5725 times 120.9 plus this percent times this mass. Let's just put an x in for that mass. We'll solve for x, figure out what that mass would be. So 0.4275 times x. I'm not going to go through the algebra with you here. I'm assuming you can do that, but remember I'd want to multiply these, subtract it over to this side. Now I'll end up having to divide by that to get x by itself. So I got an answer of 122.89 AMUs. So this isotope, and it should have been about 123, so that's right. This isotope had a mass of 122.89. 42% of them are that mass. Again, a fairly simple problem. The next one's a little bit tougher. It takes a little bit more time to do. So nitrogen has 2 isotopes. Nitrogen 14 has this mass. Nitrogen 15 has that mass. We don't know the percent of either one. Here's the average off the periodic table of all the isotopes of nitrogen in the world. So if you look at this, it's very, very close to that one, not so close to that one. So this must be a much bigger percentage of the isotopes than this one is. So we're going to solve for those. The best way to do this would be, there's only 2 isotopes, so the percentages have to add up to 100. So I'm going to make one of these X% and the other one 100 minus X, or I'm going to do 1 minus X to keep it as a decimal. So this one would be 1 minus X%. So if we get a percent here of 90, this one would be 10%. We can do 100 minus that to get the answer. So I'm going to do the same thing now. Percent times the mass plus percent times the mass equals the average. So I'm a little bit crooked. So our average is 14.0067. Average equals this percent, X, times that mass. So 14.0031 X plus this percent times that mass. So 15.001 times 1 minus X. Okay, now we do have to do some algebra here. You do have to distribute through here. So I've got to distribute the 15 through those parentheses. So when I do this, I would end up with 14.0067 equals 14.0031x plus 15.001 minus 15.001x. So I can combine my like terms, meaning I can combine my 2x terms, and I can move this one over to the other side, subtract it over the other side. Okay, so when I do that, I get, subtracting this to the other side, I get a negative 0.9943. Combining my 2 like terms, I get a negative 0.9979x. That leaves several decimal places here. Again, we're going to, sorry, that's negative. Okay, divide by a negative 0.9979 to get x by itself, negative 0.9979. When I do that, I get x equals 0.99639. Now remember, that's our percent, so we're going to move the decimal over. It's 99, we'll say 0.64%. Well, remember, the average was very, very close. The average here was very, very close to that, so this had to be a lot higher percent. So this percent would have been 99.64%. This percent would be 100 minus that, so just 0.36% of the isotopes would have that mass. Sayonara. That's my Japanese lesson for